So we're just going to look a little bit at elementary dynamics. So basically looking at Newton's laws. So the first law is that a body remains at rest or continues to move in a uniform motion in a straight line until it experiences an external force. So basically, if I move anything, if I'm exerting a force on it, it'll move. But if I don't exert a force on it, it just stays there. You can see right now there's actually a little bit of wind blowing, and that wind exerts a force on the pen and it moves. But if no forces are there, it doesn't move, it stays still. If something is moving along with no forces acting on it, it will keep moving. Things like friction obviously can slow things down, but if there's no air resistance, if we're ignoring all of those things, it would just keep moving forever at the same speed until a force is acted upon it. The second law, the rate of change of momentum is proportional to the applied force. So the rate of change, of course, is the derivative. Momentum is mass times velocity, and that's proportional to force. Now, if we choose a suitable constant of proportionality, we can actually say that the mass, just bringing the m out the front, so mass times the rate of change of velocity is equal to force. And the rate of change of velocity, of course, is acceleration, so mass times acceleration is equal to force. So that equation, force equals mass times acceleration, actually comes up a lot in the remainder of this chapter. The units there, force is measured in newtons, mass is in kilograms, and acceleration is in meters per second squared. Now, if you're not in those units, you do need to do a bit of a conversion. So that means that 1 Newton is 1 kilogram meters per second squared. Those are the units there. Okay, the third law is that for every action there is a reaction equal in magnitude and opposite in direction. Often you heard that said as every action has an equal and opposite reaction. So here's an example of what that means. You've got a person falling towards the earth. The person falling, their force is 60, if they're about 60 kilos, is 60 times their acceleration. The earth has an opposite reaction, an equal and opposite reaction. The earth is approximately 6 times 10 to the 24 kilograms. So the earth's force in the opposite direction is 6 times 10 to the 24 times its acceleration. So those two things are actually equal to each other because they're opposite directions. So you can say that 60 times the acceleration of the person is equal to 6 times 10 to the 24 times the acceleration of the earth. Or if I divide each of those by 60, the acceleration of the person is 10 to the power of 23 times the acceleration of the earth. So the person is falling pretty fast relative to the earth. So it looks to us like the earth isn't moving at all because it's such a tiny, tiny amount. And quite possibly there's something happening on the other side of the world that cancels it out too. There's all sorts of things going on there, but the earth does have that opposite reaction to the action of the person falling. In this example, a body of mass 4 kilograms is acted upon by a variable force, force equals 16 times 5 minus 3t, for 5 seconds. If the body starts from rest at x equals 0, find its final velocity and the total distance travelled in the first 6 seconds. Okay, so in order to answer this question, we know that force equals 16 5 minus 3t, and we know that the force is equal to the mass times the acceleration. So instead of force, its mass is 4 kilograms. I'm going to go 4 times acceleration is equal to 16 times 5 minus 3t. Okay, so I'm going to divide each side by 4. My acceleration is equal to 4 times 5 minus 3t. So in order to find its final velocity, I need to find the velocity equation. So we know that acceleration is equal to dv dt, which is an appropriate one to use when we're in terms of t. So dv dt equals, I might just expand this out, I don't need to, but I think I will. So 20 minus 12t. So if I integrate each side of that, so v is equal to the integral of 20 minus 12t dt, which equals 20t minus, I'm going to be dividing by 2 once I increase the power, so 6t squared plus c. And we also know that initially when t equals 0, that v equals 0. So v equals 0, then t equals 0. So 0 equals 0 plus c, so c equals 0. So our equation is that v equals 20t minus 6t squared. So the final velocity is when, so one thing in the question is that the force acts upon the particle for 5 seconds. So we need to find out what its velocity is at 5 seconds, because after that time, the force is going to stop acting on the particle. So therefore it's going to continue at that speed ongoing into the future. So to find its final velocity, we need to find its velocity at 5 seconds. So let's substitute 5 into this equation. So v equals 20 times 5 minus 6 times 5 squared. And that equals negative 50 meters per second, and that is the final velocity. So the next part of the question asked us to find the total distance travelled. So in order to do that, we do need to find its displacement equation. So we know that v equals 20t minus 6t squared. So let's go ahead and integrate that. So v is equal to dx dt. So 20t minus 6t squared. So x is equal to the integral of 20t minus 6t squared with respect to t. And that equals, I'm going to be dividing by 2 because I'm going to go to t squared. So that equals 10t squared. This one I'm going to be dividing by 3. So 2t cubed plus c. It started at the origin, so x equals 0 when t equals 0, therefore c does equal 0. You can verify that yourself. So the displacement equation is 10t squared minus 2t cubed. Now most questions would actually tend to ask the difference in the displacement at this time, but this question asked for the total distance travelled. Now if I graph that equation, I'll just do a really rough sketch over here. Let's just factorise it first. So 2t squared 5 minus t. So if I graph that, I've got a double root at 0 and a single root at 5. So 5 there. So it's a negative cubic equation. It's going to end going down. It's going to look something like that. It would go back up, but of course t can't equal 0. So the difference in displacement from 0 to 5 seconds is actually 0. We were asked for the first 6 seconds. So because it's now moving at negative 50 meters per second, it's going down 50 meters each second. So it will move 50 meters in the final second. But the question actually asked for the total distance travelled. So we do need to find how far it moves up until this maximum turning point. So to find the maximum turning point, we need to know when velocity equals 0. So velocity equals 0. So velocity was 20t minus 6t squared equals 0. Let's factorise that. So 2t, 10 minus 3t equals 0. T equals 0 is obviously the beginning, because that's a turning point as well. So this one is when this one equals 0. So t equals 10 on 3. So let's just go ahead and calculate how far it travelled from here to here. So we need to find its displacement when t equals 10 on 3. So x equals 10 times 10 on 3 squared minus 2 times 10 on 3 cubed from this equation here. When I put that in my calculator, I get 1,000 on 27. I'm just going to leave it in that form for now. Now the total distance it travels from here to here is travelled 1,000 on 27 meters. It also comes back to here. So the total distance for the first 5 seconds is 2 times that distance. And then in the final second, In the 6th second, remember it continues at negative 50 meters per second, so each second it travels 50 meters in this direction. So it's going to travel another 50 meters. So we're just going to add another 50 onto that for the total distance. And that's approximately equal to 124 meters to the nearest whole number. Okay, so in this example, we have a 2 kilogram particle that starts at the origin with velocity 1 meter per second. The particle is acted on by a force equals 2e to the negative 2x, where x is the particle's displacement from a fixed origin. Find an expression for v squared in terms of x. So that's a really great clue that they've said v squared. So we know that the force is equal to 2e to the negative 2x. And we know, of course, that force is the mass times the acceleration. So 2 times acceleration equals 2e to the negative 2x. And acceleration on its own is e to the negative 2x. We need an expression for v squared. This is in terms of x. So it's obviously logical to use that equation that the acceleration is equal to the derivative in terms of x of half v squared. And that equals e to the negative 2x. So if I integrate each side of that, I get that half v squared equals the integral of e to the negative 2x with respect to x, which equals, I need to divide by the negative 2, so negative e to the negative 2x over 2 plus c. Let's put that over 2 as well. So v squared equals, I'm just going to put the c first because it's positive. Well, it might be positive. I already know it happens to be positive. There we go. So let's find the c. So we were told in the question that velocity is 1 meter per second when the particle is at the origin. It started at the origin. So c minus e to the 0. E to the 0, of course, is 1. So let's add 1 to each side. So c equals 2. So therefore, our equation for v squared is that v squared is equal to 2 minus e to the negative 2x. So part B of this question is to explain why velocity must always be positive. So we know that initially at t equals 0, the velocity is 1 meter per second, and it's at the origin. So it's at the origin and moving towards the positive direction, right? Velocity is positive, it's moving to the positive direction. For the velocity to be negative, it would first have to equal 0. So let's just find out when the velocity equals 0. So velocity will equal 0 if the square of the velocity equals 0. So if this thing equals 0, and that happens when x gets to negative 0.35. Now, here's the issue. We're starting here at the origin, okay, and we're moving in this direction. And we keep going along here, and we keep going along here, and we keep going along here. When we reach negative 0.35, the velocity will be 0. Well, that never happens. So the particle won't be 0 until we reach x equals negative 0.35, but because it's moving right from the origin, that will never happen. Now part C is to show that v tends to the square root of 2 as t tends to infinity. So we want to find the limit of the velocity as t goes to infinity. So the limit as t goes to infinity of velocity, well, let's actually start by finding the limit of v squared as we go to infinity. So that would, because we are moving right from here, and we're always going to be moving right, velocity is always positive, so we're always moving right. That would also equal the limit as x goes to infinity of v squared. So that equals the limit as x goes to infinity of our 2 minus e to the negative 2x. Now, if x equals infinity, e to the negative infinity is 0. So this whole thing is equal to 2. So the limit as t goes to infinity of v squared equals 2. Okay, so the limit as t goes to infinity of v squared equals 2. So therefore, the limit square as t goes to infinity of v will equal the square root of 2, just square rooting each side. So it has been demonstrated that acceleration due to gravity is inversely proportional to the square of the distance to the centre of a planet. Thus, if x is altitude and r is the radius of the Earth, then the acceleration, the second derivative of the altitude with respect to time, is inversely proportional. It's negative because it's being pulled towards the Earth, so we're thinking of that as a downward movement. Some constant of proportionality inversely, so over the square of the distance from the centre. So if you're 1 metre above the Earth, then you've got the 1 metre plus the radius of the Earth. That's your total distance squared above the Earth. That value of k is a positive number. So we've got an object that's been dropped from x equals r. So its distance when it's dropped above the Earth is actually equal to the radius of the Earth. Let g be the acceleration due to gravity at the surface of the Earth. So that gravity, the closer you are to the Earth, the stronger that is, the stronger that pull. So that can actually vary as well. But we're saying g is the amount of gravity when you're on the surface. So part A is show that the object hits the ground with a speed of the square root of r times g. Now, in order to do this question, the first thing that I would actually like to do is work out what that constant of proportionality is. So we know that the second derivative with respect to time is equal to negative k over x plus r squared. Now we also know that when x equals 0, when we're on the surface of the Earth, that same thing is going to be equal to negative g. Negative because it's being pulled down. Remember, g is a positive number, so this thing here is positive too, by the way. The radius of the Earth and the gravity, both positive numbers. So let's work out what that is. So we're just going to find out what this k is by using these values that we know. So negative k on x plus r squared is equal to negative g. I'm going to, the x is equal to 0. So 0 plus r squared. So this is just r squared. I'm going to times each side by r squared. I'm going to cancel out the negatives, multiply each side by negative 1. So k is equal to g times r squared. So that's our constant of proportionality. Okay, so I've replaced the k with g r squared in that equation. Now this equation is with respect to x, so we're better off using that half v squared result because we are in terms of x. So I'm just going to kind of skip a step from what I have been doing. Rather than writing d dx on this side, I'm just going to write the integral on that side. So that's negative g r squared. Those are both constants. I'm going to write this with a negative power, and that's with respect to x. Fantastic result, that one, very helpful. So let's have a look at what that equals. So g squared is just a constant. We're going to, of course, increase the power to negative 1. We're going to divide by the new power. We're also going to divide by the derivative of the inside, which in this case is just 1, and plus a c. I'll make it a c over 2. Okay, let's just double everything. So v squared is equal to, these negatives are going to cancel out. So we've got g squared over x plus r plus c. 2, sorry. Okay, let's find out what that plus c is. So what we were told is that initially it was being dropped from a height of r, where x equals r. So initially x was equal to r, and it was dropped, so its velocity, its initial velocity is going to be 0. So 0 squared equals, that's 2g r squared over r plus r. So I'm just going to write that as 2r plus c. Cancel the 2's, cancel an r, subtract from each side. I'm subtracting this bit but turning it around. So negative g r, so our c is negative g r. So therefore our v squared is equal to 2g r squared over x plus r minus g r. Now I'm just going to write that with a common denominator. I wouldn't actually need to do that to answer this part, but it is going to be useful later. So I'm going to times that by x plus r over x plus r. So I'm also going to factorise out the gr. So v squared is equal to gr. That leaves me with the first fraction of a 2r minus an x plus r over x plus r. So I've got gr and then 2r minus another r, so that's just r minus x. Because this one has the r first, I think I'll do that in the denominator as well. So I'm just going to write r plus x in the denominator, and that's our v squared. So we were asked for the velocity when the object hits the ground. So when it hits the ground, our x is equal to 0. So v squared equals gr times r minus 0 over r plus 0. So that equals gr. So v is equal to gr. I should point out the question was asking about the speed. In actual fact here, v is going to be less than 0 at all times because the object is moving towards the ground, and we already established that our frame of reference is that down is negative. So in actual fact, v is negative the square root of gr, but the speed, of course, is the absolute value of that. So the speed is the square root of gr. So part B asks us to find an expression for the time taken in terms of x, r, and g. So this is going to be a very algebraic problem, this one. Now, as I said in the previous example, our velocity is going to be negative. So I'm going to start by saying that velocity is the negative square root. It's going to leave that gr out the front, and then times the square root of this part, which is r minus x over r plus x. Now we're trying to find t, so we do need to be integrating here. V is the same as dx dt. We do want that in terms of t. So we are going to have to use, we could either flip it or we could do separation of variables. I'll just write out what we've got at the moment. So that's times minus x over r plus x. I'm going to use separation of variables, so I'm going to multiply each side by the reciprocal of that thing, and I'm going to bring my dt up. So I'm going to end up with plus x over minus x dx equals negative square root gr dt. And of course we're going to integrate each side of that. I'm going to put my integral after that constant. So that right hand side is just t. Now in order to integrate this side, I'm going to rationalize the numerator. So I do want to multiply the top and the bottom by the square root of r plus, plus x by that numerator. I'm actually going to turn this thing around as well. I'm going to write that on the left hand side. So we've got negative the square root of gr times t is equal to the integral. So that numerator now is the square root of r plus x times the square root of r plus x, which is just r plus x. And the denominator, I've got the square root of r minus x times the square root of r plus x. That's a difference of 2 squares. So it's the square root of r squared minus x squared, and that's with respect to x. Okay, in order to integrate that, I'm just going to separate it into 2 fractions. So we've got the integral of r over the square root of r squared minus x squared, which is just a sine inverse, plus x over the square root of r squared minus x squared with respect to x. That one I'm going to use a substitution. The substitution I'm going to use is that u squared equals this bit under the square root, so r squared minus x squared. Let's find out what our dx is for that. So 2u du equals negative 2x dx. Let's divide by negative 2. So negative u du is equal to x dx. We do have this x dx in our numerator there, so it's useful to leave the x with the dx there. So we're going to be replacing that with a negative u du. Okay, so as I said, this is a sine inverse. So it's r times sine inverse of x on r straight from the reference sheet. And this one is now, instead of x dx, we've got negative u over the square root of u squared with respect to u. Okay, so that equals r sine inverse of x over r plus, this is just u over u, so that's 1. So actually minus in this respect. So minus u. U is the integral of 1. I'm just going to go straight back to putting that thing. So let's go minus the square root of r squared minus x squared plus c. Okay, let's work out what the plus c is. So we know that t equals 0. Initially, x was equal to r, so let's use those initial values to find our c. So this left-hand side is just going to be 0. So 0 is equal to sine inverse of r over r. Let's just go r sine inverse. R over r is 1 minus x is r, so r squared minus r squared, so that's just 0 plus c. I'm going to move this bit to the other side. So c is equal to the negative of r. Sine inverse of 1 is just pi on 2. So negative r pi on 2. So at this point, our equation is that negative the square root of grt is equal to, we've got r sine inverse x on r minus the square root of r squared minus x squared minus r pi on 2. We're almost there. We were asked to find an equation for t. So technically at this point, if you just divide each side by that negative square root of gr, you have answered the question. So I'll just do that. T, so this is now going to be negative r on root gr, sine inverse x on r minus, plus now because we're dividing by a negative. Let's go the square root of r squared minus x squared on the square root of gr minus, r pi over 2 root gr. Look, technically that answers the question, but I'd really like to tidy that up a whole lot more. Okay, so in order to tidy that up, I'm just going to start by simplifying a little bit here and a little bit there. I might also write this one first. So r divided by the square root of r is just the square root of r. So my first term is root r over root g for those square roots. I've also got a pi into 2 there. That's this term. Minus, let's do this one, r over the square root of r is the square root of r over root g sine inverse of x on r plus, look, I'm going to bring that, I'm actually going to see how I've got the root r and the root g on each of those. I'd quite like to have that here as well. So let's put the root g out. Let's just, to get rid of that root r from the denominator a little bit, let's just times that by root r on root r. So this root r I'm going to write out the front, just because each of those has got that as well. This square, there's still a r in the denominator. I'd like to bring that into the fraction, actually, into the square root. So let's go r squared minus x squared there. Now this was, there's a root r there and a root r there, so that's the square root of r squared. Okay, let's factorize out that root r over root g. So we've got root r over root g, we've got our pi on 2 minus our sine inverse x on plus, let's go r squared on r squared is 1, and this is x squared on r squared, and I really like that because that's also the same as what was in here. It's the ratio of your distance from the surface of the Earth to the radius of the Earth. And I'm going to leave my final answer exactly like that. Like I said, anything where you've got t equals and you've got all the variables they asked for in the question, technically you have answered the question. So if you did stop at that line, I don't really see how they can mark you down. But of course it could be a show that question, in which case you do need this middle line here, I think, to get to there. Although really I have shown a lot more steps here than completely essential. We could have reduced the number of steps a little bit, but obviously the more steps you show, the less likely you are to make mistakes. But we also have to take time into account with extension 2 because it is very pushed for time to get through the exam.